Hello, welcome. In this section, we're going to construct an equation of a plane. A plane in space is determined by a point p sub 0 with coordinates x sub 0, y sub 0, and z sub 0 in the plane, and a vector n that is orthogonal to the plane. The vector n is called a normal vector. Let P with coordinates x, y, and z be any arbitrary point in the plane, and let r sub 0 and r be the position vectors of the points p sub 0 and p respectively. Then the vector r minus r naught is represented by the vector p sub 0 to p. The vector n is orthogonal to p sub 0 to p. So we have the dot product of the normal vector with the vector r minus r sub 0 equal to the scalar 0. This equation can also be written as n dot r equals n dot r sub 0 by using the distributive property of the dot product. Either the first or the second equation is called a vector equation of the plane. Now let's consider the normal vector n has components a, b, and c, and r be the position vector of the arbitrary point x, y, z, and r sub 0 is the position vector of the point with coordinates x sub 0, y sub 0, and z sub 0. Then the equation 1 can be written in terms of these components, where n is replaced by the vector, and the vector r minus r sub 0 is represented by this vector. And by using the dot definition of dot product, we can write the equation in this form, as shown in equation 3. Equation 3 is called the scalar equation of the plane. Let's have a look at an example. We want to find an equation of the plane through the point with coordinates 2, 4, -1, and with normal vector n with components 2, 3, 4. We also find the intercepts and we'll sketch the plane. So putting a equals 2, b equals 3, and c equals 4, the components of the normal vector, and x sub 0 as 2, y sub 0 as 4, and z sub 0 as -1 into the equation 3, we obtain this equation, which can also be written as this equation. So this is the equation of the plane passing through the point 2, 4, -1 with normal vector 2, 3, 4. Now to find the x-intercept, we will set y equals z equals 0 into the equation, and we obtain x equals 6. So 6 is the x-intercept of the plane. Similarly, the y and z intercepts are 4 and 3, respectively. The plane is shown in the following figure. This is a portion of the plane shown in the figure. Now by collecting the terms in equation 3, we can rewrite the equation in this way, just by transposing the term -a times x sub 0, negative b times y sub 0, and negative c times z sub 0 to the right hand side. And this is particularly a constant. So we name it d. So the equation becomes ax plus by plus cz equals d. This equation is called a linear equation in x, y, and z. Conversely, it can also be shown that if a, b, and c are not all 0, then the linear equation 4 represents a plane with normal vector with components a, b, c. For example, this linear equation, x plus 2y minus 3z equals 1, represents a plane with normal vector with components 1, the coefficient of x, 2, the coefficient of y, and negative 3, the coefficient of z in the equation. Let's have a look at another example. We need to find an equation of a plane passes through the points P, Q, and R with coordinates as shown. If we plot these 3 points in 3-dimensional space, the portion of the plane is shown in the figure. The vectors a and b corresponding to PQ and PR are A equals OQ minus OP, which is the difference between these two vectors with components 2, negative 4, 4. Similarly, B is the vector which can be written as OR minus OP, whose components are given by 4, negative 1, negative 2, respectively. The vectors A and B lie on a plane. Therefore, the normal vector n can be obtained by the cross product of the vectors A and B. Which is given by this formula. So the vector n has components 12, 20, 14. With the point P and the normal vector n, the equation of the plane is given by this equation. Here 12, 20, 14 are the components of the normal vector, and the numbers 1, 3, and 2 are the coordinates of the point P the plane is passing through, which can also be written as 6x plus 10y plus 7z equals 50. Now we want to calculate the distance from a point P1 to the plane. Consider a point P sub 0 on the plane and n be the normal vector to the plane. And let B be the vector P sub 0 to P. And we also assume the angle between the vectors B and N is theta. We want to calculate the distance D from the point P sub 1 to the plane. Suppose the point P sub 1 has coordinates x sub 1, y sub 1, z sub 1, and the plane has the equation ax plus by plus cz plus d equals 0. Let the point P sub 0 has coordinates x sub 0, comma, y sub 0, comma, z sub 0. And the vector b be the vector corresponding to the vector p sub 0 to p. Then b can be written as shown, because the vector b is the difference between the position vectors of the point p sub 1 and the position vector of p sub 0, and which gives a vector with components x sub 1 minus x sub 0, comma, y sub minus 1 y sub 0, comma, z sub 1 minus z sub 0. We can see that the distance d from p sub 1 to the plane is equal to the absolute value of the scalar projection or component of the vector b onto the normal vector n. So if we project the vector b onto the normal vector, and the absolute value of that quantity would give us the distance from the point p1 to the plane. The normal vector has components a, b, c from the coefficients of x, y, and z from the plane. Recall that the scalar projection or component of a vector a onto the vector b is given by this formula. So the component of the vector a onto the vector b is given by a dot b over the magnitude of the vector b. So the distance in our case is the component of the vector b onto the vector n, which is given by the absolute value of the dot product of n with b over the magnitude of the normal vector n. Now the dot product of the normal vector n with b is given by the quantity shown here. Which can be rewritten in this form. Now, since the point p sub 0 be a point in the given plane, the coordinates of the point p sub 0 must satisfy the equation of the plane, meaning that a times x sub 0 plus b times y sub 0 plus c times z sub 0 must be equal to negative d. So we replaced the quantity here by negative d, as we see in this step. Finally, we get the formula for the distance from a point p sub 1 to the plane with normal vector with components a comma b comma c. Let's have a look at an example. We want to calculate the distance from the point P with coordinates 2 comma 2 comma negative 1 to the plane given by the equation x plus 2y minus 3z plus 6 equals 0. Now by substituting x sub 1 equals 2, y sub 1 equals 2, and z sub 1 equals negative 1, and a as 1, the coefficient of x, b as 2, the coefficient of y, and c as negative 3, the coefficient of z, in the equation of the plane as the components of the normal vector into the formula we just proved. And this gives 5.